Thank you very much for inviting me. It's an honor to be here. A little bit about myself. I'm a senior research fellow at the University College at the Architecture School of Bartlett School of Architecture. And I've been working for quite a few years in the industry as an architect, and then eventually I did an engineering doctorate in virtual environments. And I'm the founding director of Design Computation Limited. And I have a group called designcomputation.org, and we have a wiki on computational design, and it's something that is free and accessible for everyone. And I'm one of the founding directors of the Construction Blockchain Consortium with Professor Alan Penn and Professor Philip Treleaven. And we just heard from our colleague, Eleni Papadonikolaki. And my main interests are really design and choice, and how we decide between different options in design. And in order to understand this better, I've been looking at lots of different emergent technologies like AI and machine learning, human-computer interaction, computer-supported collaborative work, BIM and BIM, behavior modeling and game theory, ethnographic methods, and distributed ledger technologies. So at UCL, we have a number of grand challenges. They are related to justice and equality, human well-being, cultural understanding, sustainability, and cities, and global health, and transformative technologies. So UCL as a whole is looking a lot into food security, inclusive growth, future of work. That's a very big topic with machine learning, climate change, finance, the internet, and what the internet will become with new technologies, global trade and investment, and long-term investing, and with the fact that we are living longer, and healthcare in the future. Two things that are very relevant for us is like sustainable cities, of course, and the transformative technologies. So I'll talk a little bit about the work I've done on build information modeling and how I've been using build information modeling on my consultancy on design computation. So I was very privileged to work on some very challenging but very interesting projects, like the Apple campus in California, the Google campus in California, the Google campus also here in King's Cross, a very complex, geometrically complex project, The Vessel by Thomas Heatherwick, a very interesting project, and also the Royal Theatre of Rabat. We heard a little bit about the theatre this morning. Used to collaborate with the engineers on that. And what is very interesting about BIM, in my opinion, is that BIM, as it is presented today, is it's a kind of a visual object-oriented programming. It's very data-rich, and in BIM we have things like placing objects, embedding, open and close objects, in place and adaptive modeling. And akin to this, we also have in object-oriented programming things like abstraction, inheritance, encapsulation, and polymorphism. And but this is not so intuitive for the designer. It's a very different way to design and compose your build information model. But it is a kind of parametric object orientation, and you place objects into a project environment, and you compose a piece of architecture, a building, and eventually use this information to do facilities management and to recycle the building. With the development of BIM, we start to do things like simulations and reporting, like energy simulations. This is the canopy of the first phase of the Google campus in Mountain View. So the first phase is called Charleston East. And with the simulation and reporting, we get this ad hoc feedback on the different options, and this guides us through the decision-making process. So we came up with lots of different strategies to place solar cells on the different modules of the canopy. And it was in a kind of assisted decision-making process by the software. Akin to this, we have also the collaborative tools that we see emerging in different BIM platforms. So on this particular project that I helped, something was they spoke of a master plan just outside Moscow, and it was something that I worked with Valodin Pist in Paris and the Arup team here in London. And was a very large team, collocated. Everybody was working on the same floor at Arup here in London. And we could very quickly visualize who was doing what and what sort of work set they were working on, what they were changing on that work set. And by using the build information model, we could set up very quick meetings to clarify what was going on. And on this particular project, we had the architecture team together, sitting side by side with the engineering team, and it was incredibly productive. So going back to the Google campus, one thing that we realized was problematic was the gradual handover of the design architect model to the delivery architect. The delivery architect for this first phase of Google was Adamson in California, and we had to develop this kind of a ghosting method where they would have access to our build information model and gradually rebuild everything, although we were pretty sure about what we were doing. And we all thought this was incredibly wasteful. And I start to think if there are better ways to do that. This slide really breaks down on a longer presentation in many slides showing how this ghosting method was deployed. But basically, because the build information model was very complex, they decided to rebuild it so they could understand exactly what was going on. And I think there is a huge inefficiency in that. Yeah. Something else about build information model is the interoperability strategy that we have to think about. Of course, this is gradually disappearing. We are connecting data in much better ways, but there is an obstacle there. And when we start to look at the interoperability and this object-oriented way of modeling, we can start to see that blockchain would be a technology that would be very helpful. And with the implementation of blockchain in build information modeling, we also come up with opportunities to better protect our intellectual property. So I think at the moment, I think most people here would agree that build information modeling is very front-loaded. Architects and engineers, they have to work extremely hard to compose a reasonable build information model. But eventually, we create this parametric knowledge legacy for the project. And there is an increase of knowledge and intellectual property that we need to protect. So we'll talk a little bit about emerging disruptive technologies. I'll be very brief. But I think nowadays, and especially today, we've been talking about a number of interoperability challenges. Things like cloud computing, concept simulation, computer-supported collaborative work and design, assisted decision-making, big data, metadata, or data in general, programmatic design, things like generative design and scripting design in different forms so you achieve high efficiencies on managing change, reality capture, virtualization, and building management systems. These are, I think, I might be missing something, but I think these are the main things that we have to improve in terms of interoperability and linking data and making data more transparent across all those different applications. And the emerging technologies are things like the Internet of Things, as a covert term, artificial intelligence, including neural nets and machine learning, deep learning, etc. Distributed ledger technologies, virtual environments, computer-supported collaborative work in general, human-computer interaction in user experience, and automation in general, like digital technologies and so on. Like blockchain is something that we can generally classify as under a distributed ledger technology. And there are lots of synergies between them. So when you improve a feature or come up with some new technology for one of those categories, they will affect how the other technologies are used. So that we kind of has to, one would have to cross-map the interoperability challenges with the emerging technologies. Then I'll focus a little bit on the blockchain technology. So as my colleague said previously, we have centralized databases, decentralized, and distributed databases. On distributed databases, you can set up something called a Byzantine fault tolerance. And this is simply creating public and private keys so you can hold to some data and be able to modify that data. And you can give a public key to somebody else to just observe or have access to that data, but not necessarily change the data. And this is in the field of cryptography. So 3 very key characteristics of blockchain are it's resilient distributed ledger. So by resilient, I mean, it's not to say that a centralized database is not secure, but if the person who controls that centralized database decides to switch the database off, nobody else can do anything about it. So you won't have access to that database. You will have access maybe to a copy of the database somewhere, but it's not as that you can carry on working. Let's say if you have a common data environment and that common data environment is switched off, what can you do about it? The other thing, this wouldn't happen on a distributed ledger database. So immutability is the fact that once you create a block, what is resisted or what that block is pointing to cannot be changed. So in essence, what you're doing is giving physical properties of the real world to digital assets. So for example, if I have a picture and I blockchain that picture and give that picture to you, I will no longer have access to that picture. Yeah? It can be designed in that way. And you can also guarantee provenance. You can guarantee that that data came from that person and nobody can tamper with the data. So with this, you have, to make blockchains, different blockchains work, you have like a few different things going on. So you have, normally if it's a tokenized economy or if it's a tokenized blockchain, you'll have a mining process. You will have to have a proof of work, which is normally a small puzzle to avoid cyber attacks. And this puzzle has to be computationally costly, so people don't simply go there and keep doing funny things to the blockchain with no consequence. And often you also have a proof of stake. In early blockchains, you don't really have a proof of stake, but or you do have a proof of stake, but it's not so robust. The newer blockchains, they are investing quite a lot on making the proof of stake more sophisticated. So, for example, if you using Bitcoin, Bitcoin is mainly a unit of value, and there is a work you have to mine for that value and create the block. And then there is this proof of work is solving the block. And then if you solve a block, then you get a payment from the blockchain. I think you get, nowadays you get, I think, 7 Bitcoins or something like that, or maybe more, 17 Bitcoin. So over time, the payment that the system gives back to you, the creation of new Bitcoins will decrease. And eventually, I think in 2075, all Bitcoins will be generated, and your proof of work will be, the payment for your proof of work when you're mining for blocks will have to be paid by the person creating the transaction in the Bitcoin blockchain. And some implications are, the application of blockchain have some implications. They are cultural changes. You know, things will operate in a very different way. Some say that a blockchain will be the new internet. And you can create things like very sophisticated smart contracts. And you could have a much better control over supply chains. And you can have something called distributed autonomous organization. So you could create an intelligent agent that will be executing payments, mining, and also creating blocks and so forth. And that's a very complex topic, and maybe we could talk in detail on our drinks later on. On different blockchains like Ethereum, you have, it operates slightly different. You have something like Ether, which is a unit of value, and you have gas. Gas is a unit for work. And when you're creating your transaction in Ethereum blockchain, you can decide how quickly you want work to be done, and then you would pay for that work to be done quicker or slower. And then you also have your exchange of value. And by doing that, you have a distributed application running on the internet. And you can create smart contracts using a very domain-specific language called Solidity. Solidity at the moment, I didn't use it very much, but at the moment seems to be fairly simple, and it's just starting to become something more sophisticated. So, well, I can talk more about blockchain later on, because it is a very big topic. And I'll talk a little bit about the research I've done with teams and collaborative design. So I've done a number of experiments at a university college, including ethnographies, going around offices in London and observing people, interviewing them, and so on. But also controlled experiments on a controlled lab using software and hardware I've developed myself. In one of the control experiments, some of the data I collected include sketches to change a scenario. So was a digitalized planning exercise where two architects would sketch a solution, and we had the control session and the experimental session. On the experimental session, halfway through the design process, we changed the scenario. We include some piece of extra information. And by doing that, we changed their behavior. And what this interface and the software was doing was basically capturing everything they do. So was counting the number of vector space catch, seeing how long they were taking to create a sketch, and time stamping all this. And my hypothesis for this particular experiment was a falsifiable question. Basically, I want to know if by adding the extra constraint when they were designing, when they already had formulated a solution for that design constraint, if they were to increase or decrease critical production, if they would have to come up with more ideas, or if they would just leave it or make minor modifications because of the time pressure. And there was a very strong correlation between adding the extra constraint and increasing critical production. So we got a very high significance, a p-value of 0.008, and this is very, very significant. And although this was a very simple experiment, it shows that by giving information at the right time to the team, they can actually come up with something better. I had other two hypotheses, but they were not as significant as this one. And then I started to look at different ways to model design interaction. And there are many models out there. So you have the classic Gabriela Goldschmidt from the 1990s, linkography. And basically she's trying to capture the ecosystem of good ideas and how good ideas come back to the design as you play the design process. And John Giro implemented a lot on this original idea, and it's really fascinating. The work he came up with is really seminal. It's remarkable. And then we have more prescriptive models like Thomas Ekman and Gray and Hughes. And then all those models, they are either prescriptive or descriptive. They are either looking to improve the design process by prescribing a method, or they are observing what we do. What I've been interested on is how you can actually design the interaction. So to create interactive models, you need to look at human systems, and you need to look at, in particular, the teams. And there is a difference between virtual teams and collocated teams. I've been looking recently more into collocated teams, people in the same room designing together and using digital tools. And if you come up with a good interactive model of the design process, then you can transform that model into a predictive model. So for that, to model the interaction, you need to play with game theory. Game theory is a type of economical modeling that looks at the behavior between two or more agents. If you want to look into how one person makes decisions, how you decide what clothes you're going to wear in the morning or what you're going to have for breakfast, then you look into things like behavior economics or risk and prospect theory. Game theory is more for multi-agent modeling. In game theory, we have quite a few different things. It's a complex area of economics, and I'll try to make it really brief. So for game theory models or interaction models, you need a utility function, you need a best payoff, you need some sort of motivation, you need some sort of equilibrium, what makes you make that choice given the utility you have. And when you have that, you have a dominated strategy, and therefore you can predict, you have a backwards induction. The predictive formulation of game theory is called economical mechanism design. So I'll see if, so here we have a classic coordination game. So you have a player one, player two. Player one can go up or down, player two can go left or right. And then you have utility. So if player one goes up and player two goes left, each one gets 1 point. But you have like a dominated strategy here. So for whatever reason, when you create this coordination game, if player one goes down and player two goes left, player one will get 2 points, player two will get 1 point. And therefore, the dominant strategy for player one is to go down. And the dominated strategy for player two is to go left. Yeah? And this becomes more complex. Yeah? So von Neumann was the mathematician who came up with game theory. And John Nash, very famous John Nash, came up with the Nash equilibrium, which is widely applicable in game theory and in many other economical models. And he won the Nobel Prize for that. It's a really brilliant, incredibly simple but brilliant idea. So in game theory, you also have different levels of complexity. They can start very simple, like a complete information models, when everybody knows what everybody else playing the game should be doing. And then you have, and then there are static games. For example, you make a choice, the other person you are working with or collaborating with also makes a choice, and then the game is over. So it's a one-off game, it's just one decision. And then they can become dynamic, so we have many steps. And then they can be of complete information or incomplete information. And eventually, when situations are very large and complex, they become imperfect information. So in game theory or in behavior modeling in general, you have this distinction between perfect and imperfect information and complete and incomplete information. And this has to do with knowing the rules or not knowing the rules, and knowing that everybody knows about what needs to be done, and not knowing if other players know what they should do. Okay, so I need to speed up a little bit. So, and then I came up with a model based on a very known model in economics called the centipede game. It's a simplified version of the prisoner's dilemma. And I modified this game to try to understand how value is articulated in design teams. I can explain this in more detail in some other occasion or outside. And by collecting user stories, particularly from the Google project, and how they were using Beam 360 and Revit and so on, I tried to look at the metadata and spot how collaborators were exchanging information and how I can apply this game theoretical modeling to their decision-making process. And then now, with the advent of the construction blockchain consortium, I'm trying to use a similar process to blockchain the decision-making process, and therefore come up with a more efficient way to protect how people do things, what they are doing, and how this can benefit later projects. So keeping the data that you generate, your parametric knowledge alive and usable for later projects. Something that I've been working recently is on a machine learning method, a convolutional neural net, to automatically understand what an object is within Revit and how this can be used to know what people have been doing and where that family is coming from. So that's very early days. And it's working really well. So the confusion matrix is becoming very clear. So very quickly you can identify what an object is by, and you can use dumb geometry. You don't need to use, say, a Revit or ArchiCAD object. You can wipe all the metadata. You can make the geometry like a DXF or whatever you want it to be. And by just looking to the vectors, you can find out what object it is by the geometrical configuration. And the future research will be really into investigating more what we can do with the Internet of Things and how we control this with some more lightweight blockchain technologies such as IOTA, machine learning, and how by using blockchain we can make the data more machine readable and therefore easier to learn what's going on or see patterns on that blockchain and how this integrates with BIM. So I'm looking at things like IFC, Ethereum, Steam, Neo, and Bitcoin as well, but Bitcoin seems to be more interesting for only value exchange, not so much the execution of work. It's more for the value exchange, the occasional value exchange. And this is my presentation. If you have any questions, let me know. Thank you very much.